Hello everyone. Today I'd like to talk about general relativity with the headlights on. Video number 1. So first question, why relativity? Why are we not happy with Newton? Because I was told, even at university I was told this, that Newtonian physics works acceptably well for the traditional low speed phenomena. You have to get up to very high relativistic speeds before it becomes important and you can just ignore it. Well, it's true that it functions within its scope, which is actually low speeds and weak forces. But once you get to higher speeds, excuse me, or stronger forces, then Newtonian mechanics fails. Now here comes the problem. The electric force is a very strong force, which in practice assures that Newtonian mechanics fails totally, even at very low speeds for electrical phenomena. And this means that it totally fails to explain our common electrical devices excuse me, such as cell phones, transformers, magnets, and others. It turns out that the only long-range force, and by that I mean greater than 10 to the minus 18 meters, so basically the only force that we're going to experience other than gravity, and that's with the possible exception of gravity, the only force we're going to experience is the electric force. The electric force is certainly the only strong long-range force, and it is so strong that even at minute speeds, and I'm talking about a few millimeters per second, literally the speed at which a snail travels, relativistic, in other words, non-Newtonian forces, are physically significant or even dominant. So it turns out that electrons moving in a conductor move at these slow snail speeds, barely a few millimeters per second. And if you have like an electrical conduit and you make the electrons, let's even travel at 10 feet per second, or let's say whatever, much more than the snail speed that they travel commonly. The electrical conduit from the resistance will get so hot and it'll vaporize. Now, even if you use superconductors, you'd think, I thought, I looked it up because I wanted to know, even with superconductors, the electrons, if they go beyond a certain speed, which is not very much, I think it might even be less than the snail speed, the superconductor becomes not a superconductor due to it gets out of its resonance. Anyway, it resonates and steers around electrons, so the atoms, so it doesn't bump into anything. And this effect dissipates at very low speeds. So when you're inside solid matter, like conduits and semiconductors, that sort of thing, the speeds that the electrons travel are very slow, surprisingly slow. For example, it may interest you that when you turn your light on at the light switch, commonly you think the electrons go through the switch and into the light and then around and back. Well, it turns out that we use AC current, which is alternating. And at the speeds which the electrons travel in the conduits, the conductors, they barely move, let's say, more than a millimeter, and then they forward, and then they go back, forward and back, forward and back. So the electrons never actually cross the light switch. Even when you close the circuit, they don't go to the other side. So that is very interesting, probably surprising. So Newtonian mechanics cannot explain magnets, and they cannot explain induction or inductors. And we live in an electronic age, and consequently, we really need to upgrade our model of reality. Now, I ran into this because I did a mechanical undergrad degree, BSc, and then I did a master's in electrical engineering, and I was never, I hate to admit it because I don't like to admit things like this, but I never really could get my head around how in detail an inductor worked, and magnetism, how in detail it worked. I even went to a physics professor and I asked him, can you explain to me, why an electron, when it's traveling in a certain direction through a magnetic field, it gets a force at a right angle to its direction of motion? And I said, when I'm jogging down the sidewalk, and the wind is blowing, I don't, the faster I go, I don't go sideways onto the road. I get like a resistance in the front related to speed. And in magnetism, it's actually a transverse force sideways in a magnetic field for an electron. And the professor thought for a second, and then he said to me, don't ask that question. Which drove me nuts. I mean, that's when I started drinking coffee, because I couldn't stand to do what he said after that, which was just do the math. I mean, you'll find here that I'm not even going to put you through that. I'll talk about that later. But so I needed to understand things. It's my nature. And so I had to abandon Newtonian mechanics, or at least, let's say, extend it beyond its natural scope, which is basically, in a modern electronic world, it hardly has any scope at all that's applicable. So anyway, what did I miss here? Yes, sirree. Einstein was not satisfied with general relativity, and he was trying to unify it with electromagnetism. And I do think that it makes sense to have such a unified theory to extend and be able to replace both general relativity and quantum mechanics. So in this first presentation and the subsequent presentations on this same topic, I hope to succinctly explain general relativity and begin to demonstrate where quantum mechanical processes are at work in producing the effects within general relativity. So I'm preparing the way, but in this series of presentations, I don't know whether it's going to be 5 or 6 or something like that, but of that order, presentations, I want to reproduce all of the details of general relativity in a way that what I call the headlights on. I have some more to say about that later, which is now. Einstein felt, and he shared that for decades he felt like he was a blind man groping in the dark. And many early students of general relativity expressed the same sentiments. And even, what's that guy? Professor Dr. Leonard Susskind. He is that series. I watched most of it. And then I watched follow-ups in which he was, Dr. Susskind was saying, oh, I'm sorry that it's not more interesting. And he was doing a beautiful job. One that I want to do similar after this series. But I'm not going to do that same thing to you guys during this series. The traditional, which is to say, the traditional approach starts by teaching the manipulation of the mathematical notation, with really not casting any light on what's going on. And this leaves most students feeling that they are operating blind, much as Einstein felt he was operating blind. So in this series of presentations, I'm going in with the headlights blazing. I'm going to make everything tangible and visual. And I will be appealing to the visual centers of the mind, which in many cases are far more capable, having evolved earlier and more completely than the symbolic thinking which now dominates our lives and our academics. But the symbolic thinking is much slower and more cumbersome. It is my hope that not only do you come to a fresh and deep understanding of relativity, where you can see it in your mind what's going on, but that you also develop in the process, kind of like I did when I was doing this, a deeper friendship and working partnership between the symbolic and the talking centers of the mind, which are very close to the mathematical and in the Broca's area of the brain, mathematical and speech centers. The talking centers of the mind, what I call, and the silent but immensely fast and powerful visual processing centers. So here I just have a kind of humorous, but true, I'm not joking about this, where I have a rock going around the earth and the rock says, "Help me, I don't know how to behave. I need to go to university to study differential calculus." Well, I did go to university and I studied differential calculus, and I hate to admit it, but I actually love it. I had an Indian friend who he used to say to me, I hope you don't mind me talking about certain parts of the human anatomy, but he told me, he confessed, he said, and he was very good at mathematics. He says, "I love mathematics." Reminder, I'm not going to do that to you. But he loved mathematics. He says, he was telling me this when he came out of a calculus test, and he said, "I love mathematics. I feel it in my balls." So, now I'm not going to tell you whether I do or not, but anyway. But anyway, that's, I did the calculus, and that's not what I'm going to do to you today, or for the next 5 presentations or so. So, just joking, actually, I know how to behave, and the Stones know exactly how to behave, and they didn't go to university, but they know better than most doctorates exactly how to behave in exactly all the ways. So here the Stone is telling us, just listen to me, and I will tell you everything about it and more. So I find physics is actually like that. If you focus on the actual physical phenomena and just ask yourself, what's going on? And you want an answer that's not sort of or metaphorical in the sense of an analogy that's anything but 100% exact. I'm talking about identity. So you look at something, you say, what's going on here? And ask it to tell you what it is. And more often than not, you'll be surprised, you get an understanding that's complete, and it deals with an identity that cuts through all the mathematics and gives you immediate or instantaneous comprehension, deep comprehension. And we see this with Einstein when he was riding in an elevator, and he realized that when the elevator was accelerating upward, the light would come in and go straight, but to the person in the elevator with the acceleration, it would curve, it would drop down and hit the far side of the elevator lower than when it came in. And so that's an example of, you just ask the elevator, he perceives what's there, and then he understands that acceleration is space-time curvature, and the light will fall in a gravitational field. All that from an elevator. And then Einstein had many, many discussions with trains. And you wonder, what, did he love trains? Was he a crazy kid who had like 100 train sets in his house? No. He just, the only job he could get at the time was in the patent office, and they were working how to synchronize the train systems that were developed in Europe at that time. And they needed to know how to synchronize their clocks. And so there was a patent that had to do with sending light signals. And if you just follow the arithmetic and you're honest about the problems that you encounter, you have to come up with special relativity. So it's kind of a fortuitous gift from fate that Einstein was working in that patent office, and he had to deal with these very tangible issues that sort of led the way for him to enter into this realm. So we're going to do that. We're going to pay attention to the physics as well. So I'm going to be using mostly images to communicate in here. So I'm going to be talking the right side of your brain. In most people, the image processing side, and cooperating with the mathematical side just to write down. But I'm only letting it use in this series of presentations the operations plus, minus, multiplication and division. Basic, in other words, basic arithmetic, the kind you use in a hardware store when you're, adding out the bill. That puts a lot of, but I loved it, but it made it much more difficult for me to go through, but I loved it. And hopefully it makes it easier for you to visualize what's going on and get a pretty darn accurate understanding of what it is. And then perhaps in a later series, I'm planning to do the traditional approach with advanced calculus and tensors, which I actually love, but most people don't love in the same way, probably for good reason. At least I find it's better to go through and understand it visually, and I hate the word intuitive because it implies that it's not accurate, but that's not true. A lot of the times, the only way to get an understanding is, a true understanding is to, ask the phenomena that you're dealing with, what is going on? What are you telling me? And that's otherwise you can get off on a mathematical tangent. In the mathematical world, you could take a small town and pile up all the mathematics books in the world, and it would be about 3 or 4 feet deep. Solid mathematics books. And most of that mathematics will not apply to general relativity. So how do you select which one? Well, you select it by focusing on the physics. So we're going to do that here. And here's an example. As a physical experiment, I take a piece of paper and I draw a line using a ruler. So it's very tangible. But on the bottom, that space, which anything in matter, like a car or you go for a jog, matter can only go in one direction. I had a very good lesson to this. That's another thing. Physics will teach you one way or the other. And in this case, we had a 5-acre property out in a giant estate with roads going everywhere, and I was rollerblading, and I came to a sort of a road, a dead-end road with nothing on it, and I thought, I'm going to go with my daughter and my wife and my son, and I thought, I'll take this moment just to do a sprint on my rollerblades down this dead-end road. And I got really going. I can go like, I hate to say it, brag or whatever, but very high speed. Let me just say that. Anyways, just got up to speed, and I heard my daughter call me, and I turn around, and there's a giant pit bull growling at my daughter. So my body and my mind wanted to go the other direction, and I tried, but that's where it comes. Physical matter can only go in one direction at one time. So I had a good reminder of that, landed from, like a dive on my belly, and that confirmed what I had suspected, what I tell you now. So we can represent space by only one direction because matter can only go in one direction at any time. So this is what I have here. So my experiment is valid up to this point. Because I've drawn a line on a piece of paper. It's a physical line, and I'm drawing a physical space which this line moves across. But I have time on the vertical dimension, and that requires us to imagine something. So it's not 100% physical experiment. But what we see here is a straight line in space. I ask myself, what is it? And it tells me I'm a straight line in space and time. Constant velocity. Rate of change in velocity equals 0. Acceleration equals 0. I go, okay. So next, I draw a line with a curve on it. Same thing, one direction in distance with space, another direction in time, which we're kind of having to imagine because it's not actually it's going in another spatial direction. So, and I say, what are you? This red line. And it says, I'm a curve in space and time. You can read it right off the chart, space and time. So, and then I just make a slight compaction of that. And I say goes to space-time curvature. So I'm a curve in space and time. Space-time curvature. So it's saying, I'm space-time curvature. And I go, okay, yeah, you're curving in space and time. True. Then the rate of change in velocity is the acceleration. Because if you start in a car and you're going at a certain speed, which is a certain time, a certain space, and then it slants over like that more and more, it's going more in space than time, then more again in space than in time, so it's accelerating miles per hour, greater and greater miles per hour, more space per time, right? So then I asked it again, what am I? I'm a rate of change in velocity equals acceleration. And then from before, equals space-time curvature. So you're performing thinking almost like a person with Asperger's or some special condition, which we can cultivate and helps us to understand these things. And so it's telling us, this line is telling us, acceleration equals space-time curvature. In other words, it's an identity. It's not like I have a bank account in one bank and somebody else has a bank account in Sydney, Australia, 24,000 miles away, or 12,000 miles away. And it's the same amount by coincidence. No, this is an identity. You take the equal sign as an identity, like Einstein did, where he said acceleration is equal to space-time curvature. I'm doing the same thing from a line on a freaking chart. So, okay, now we know from Newton that the force is equal to mass times acceleration, which means that the acceleration, you just flip it around, you get the A here, and is equal to force divided by mass. Now we have acceleration above that, and on the line we just said it. Acceleration equals space-time curvature. So we have acceleration is equal to force divided by mass, and we have that means that space-time curvature, which is acceleration, is equal to force divided by mass. Same thing. So I put in this summary at the bottom, space-time curvature equals, like it's an identity kind of equal, force divided by mass. So this is very interesting because Einstein discovered this. This establishes that the trajectory is independent of mass. Now the space-time curve is something where if you had something moving along without any forces acting on it, it would follow that trajectory. It's a curve in space-time. It's the straightest line you can go, and that's what things do when they're not don't have forces acting on them. So this space-time curvature, which is the trajectory, is equal to the force divided by the mass. So, which means that the trajectory must be a property of the space-time and not a property of the mass. How you know that is because you have space-time curvature on one side and you have equals force divided by mass. And so if you have a constant space-time curvature, for example, you have a constant ratio of force divided by mass, which means that you increase the mass, you increase the force. You increase it more, you increase the force more. So it's not the space-time curvature that's changing, it's the relationship between the force and the mass. So it's a property of space-time, not a property of mass. Mass. So at any time when you need to think about something like this, and you might want to think about this one, you can always do a screen save and then look at it later, ponder it. And I think if it was me, I'd have to do that because not everything sinks in right away, and I'm trying to say it forcefully enough, or play it back and forth a few times. So now let's look at this again and see what we can do with it. We just established that space-time curvature is equal to the acceleration is equal to the force divided by mass. Okay, I'm going through the derivation below here, which is just arithmetic. That means that the mass divided by the force is equal to 1 over the curvature. Mass is equal to force divided by curvature. Now, mass times the speed of light squared is equal to energy. And that's going to be equal to the force, because remember above I've got mass is equal to force. Well, energy is going to be equal to the force the mass squared times c squared, which is equal to the force times c squared divided by the curvature. Very simple arithmetic type of argument I have here. There's nothing complicated in there. And that's equal to the force equals the force times c squared divided by the acceleration. Again, the curvature is equal to the acceleration. So the next line says energy divided by volume. So I've introduced a volume with which the energy is distributed within evenly. Let's let it be even. Is equal to the force times c squared times divided by A and divided by volume. So when you do that, you get that the energy divided by the volume, the units are kilogram meters squared divided by second squared times meters cubed, and that's equal to, you do a little cancellation, a kilogram divided by second squared divided by meters, and that's equal to the pressure. So we get that the energy divided by the volume is equal to the pressure. That's a very, very, very deep statement. I'll say it again. The energy divided by the volume is equal to the pressure. And that would be the pressure in the volume. Now, we got all of that. Let me just remind you, we looked at a straight line on a graph, and then we looked at a curved line. And from that, using a special kind of thinking, almost like an autistic person, which demands an equality for a physical phenomena, where we get energy divided by volume is equal to pressure, which is a very deep thing. Now, it turns out that if you're going to make matter, I'll tell you how you make matter. And again, it's a thought experiment. My thought experiments. My mind just produces thought experiments. You wouldn't believe it, all day long, all night long too. And this one is, you take two mirrors, and there's special kinds of mirrors. They don't weigh anything, and they have 100% reflectivity and accuracy in the direction. And you go in space, and you start with these mirrors at a pretty good distance. And then you get inside the space, you know how there are fluctuations, Heisenberg uncertainty principle, and you get particles popping out, you get photons popping out. Oh, a photon, let's say, or a number of photons, doesn't matter, bounces off of one of the mirrors. Now, you start moving the mirrors closer and closer together. The photon hits the other mirror and takes some of the momentum from the mirror pushing it. This is a fact. And then it bounces forward. This would actually work, but in real life it would die down because they get a certain amount get absorbed. But I'm saying that you have a perfect mirror somehow. And that photon then gets blue shifted a bit, which means more energetic, shorter wavelength, goes across and hits the other mirror, which is now closer, and bounces off of it. It gets blue shifted again, more energy. And over time you keep compressing, pushing in. That photon energy and the wavelength gets shorter and shorter, the energy goes higher and higher. Now, it gets up to, let's say, 1 million electron volts, thereabouts. And something really cool happens. The empty space at that energy level pulls apart into an orbiting electron and a positron. So you've just created the first step of matter. Now let's say you keep pushing this mirrors, and the energy goes up and up and up. You'll create the next. You end up creating protons and other nuclear particles of great ever increasing mass. So you're creating matter just by compression. Now that part of your brain, I want to turn it on again. Compression equals matter. Okay, space-time compression equals matter. Now we drew a line on this chart, a curve on a chart. We got energy divided by volume equals pressure. Energy divided by volume, so that's an energy distribution in a volume. And that's mc squared distribution in a volume. It's matter. distribution in a volume is equal to pressure. And I just did the same thing talking about two perfect mirrors in space and a vacuum fluctuation, and you up the energy of the photon by bouncing between these two mirrors, compressing the space-time. And I got matter. So this is a deep, deep principle. And perhaps you want to go through this a few times and let it sink in a bit. Thanks for listening. I'm going on to the next here. So there's another thing about space-time and the vacuum itself. The vacuum, which you can do experiments on, because the vacuum has properties. Like I did my master's in electrical engineering, and later I designed both electrical components and electrical circuits, and I was always using capacitors and inductors. And when it comes to like a capacitor, you have the E naught, which is the capacitance of free space, farads per meter. And you have the inductance of free space, henries per meter. And so you go, what the heck? How did people determine that? So I'm showing here, and I don't want to go into all the details. I'm doing that somewhere else, and I have it in a book I'll probably publish soon. But I want to show it to you. It's basically, you can take two plates and separate them apart and vary the distance. And you have two areas, and you can measure the capacitance of free space doing that by how much voltage you need to put a certain amount of charge on that certain amount of area of space. And when you do that, and I'm not going to go into the details of that here, but you measure. You can do this in your garage, and I drew somewhere else. I drew this whole thing out, like I did here. And by the way, that capacitance of free space, they call it permittivity. It's like you have a little policeman there with giving you tickets or something. I don't know why they make names up like that. It's the capacitance of free space. The units tell you that. Farads is the unit of capacitance per meter. Meter distance, because it changes with the distance. If you get closer and closer, the capacitance goes up. So the capacitance of free space, when you measure it, is, and you can do this in your garage, 8.8542 times 10 to the minus 12 farads per meter. And so that's the capacitance. Empty space also has an inductance per meter, per unit length. There's an inductance, and you can measure that. And I also, these are my diagrams. I'm showing how you can do that in your garage. You have a pipe and you have a power supply that energizes a current flowing, a DC current, in one conductor, and then you have another, and it's hanging with very thin wires, so there's hardly any resistance to swinging. And you have another stationary cable that's in two vices, and it's powered DC in the opposite direction current. And those two conductors will push each other apart. And you can make them 1 meter long, so it's henries per meter, so you get the henries, the inductance. And you can measure that from the angle, because you know what the weight of the thing is, and the angle tells you what the force. So you can calculate the repulsive force, and that gives you the inductance. So again, I don't want to go into details. It's very simple, but not here. I don't want to take the time. But what it does is it gives you the inductance of free space like a component, like something you can order from DigiKey, and you get in the mail, capacitor. And you can actually make circuits on them. Now you say, well, who would want to make a circuit out of empty space? Well, who would want to do that? Let me get my cell phone. See this? Any of you go on there and play with it and get information and talk? You ever use this? Well, that thing is designed. It has an electrical circuit that plugs into empty space, and uses that circuit to send electrical messages back and forth. So we're doing it all the time. One way or another, I'm using it right now on my computer. I'm sending messages, through across the space in my house to my router, and then out, and God knows where it goes into some cell tower. We're connecting. We're using these electrical properties of space, and we're designing circuits that plug into those. So this then is telling me something. It's telling me something, and I hope I have it here. Okay, so let's see. I want to find out where that is. Okay, so I'm going to show here a circuit that designed as a common IC oscillator. So you put these values in, the ones you measured, and you find that it oscillates at 299 million and some odd up here. I'll put it in red. Million cycles per second. And then you build a bunch of these, and you put them end to end, and you could do that. You could actually simulate this in a computer, because now the simulations are accurate. You put the values in for free space, and you'll get a wave that propagates from one of these circuits to the next circuit, at 299,792,458 meters per second. And this just happens to be the speed of light. So what this tells us is that the speed of light is the only speed within the vacuum substrate. In other words, anywhere you go, you can measure the inductance and the capacitance of free space, and you'll always get the same value. So you know that light in the free space can only travel at that value, which tells you that the speed of light is constant and the same value for anyone, no matter how they're moving, what the velocity of the person or the measurement device is. And this is one of the tenets of relativity. They say, oh, light has this magical property where it's, the constancy of the speed of light. Well, you just take these simple measurements that I showed here, do that in your garage, and you've just proved it. You know that light for everybody, because I can take these apparatus here, and I can take it with me, and I can go on a rocket ship in outer space, and I'm traveling along, and I take my measurement. I'm going to get the same values. So when the light goes by one person, he's going to measure it, see it at the speed of light. He has to, because it can only go in that reference frame with these measurements at that speed. Then it goes out to the rocket, which may go at a different speed, and that guy has done these measurements, and that light wave can only go at that speed there as well. So it's one way to get at this. You don't have to take the speed of light as some kind of input. You can generate that as an output. This is a proof, and you can do it in your own garage. So here I'm saying again, emphasizing, light speed is the only speed within the vacuum substrate. Now, people go, oh, well, light is just weird. I mean, I thought that for a while. It's really weird that no matter what the relative speeds are, they always have the light go the same speed. You'd think that like if you're driving in a car and you shine your flashlight ahead of you, you'd think that the flashlight light would go the speed of the car plus the speed of light, But no, it's just the speed of light. Because the light is moving within that vacuum substrate, and it has the same capacitance per meter and the same inductance per meter, so it has to only go at that speed. Now that's profound enough in itself. But how about this? It also means, because our physical bodies, our house, our car, everything is also vibrating through this physical substrate. So we are going at the speed of light. So everything vibrates within the vacuum. It doesn't vibrate through the vacuum by pushing the vacuum aside. No, the vacuum has when I work out the bulk modulus, which I'll do later, the bulk modulus with an acceleration factor in it, is very high. So it behaves as if space-time, the vacuum of space-time, is very stiff. And you don't push things that are stiff aside to move through them. You vibrate through them. And it's stiff enough to match impedance, match the vibration, and you go right through. And we don't even know it's there. We're like the fish. You say to a fish in the ocean, well, how's the water today? And the fish goes, water? What water? Well, people hear that joke, and it's like they laugh. It's what a silly fish. Well, we're in this vacuum substrate, and we're vibrating through it. And it's a lot stiffer than water. And it's a lot more pervasive than water. And I'm telling you this now, and if you're like me, you'd say, oh, what? We're vibrating through this medium. What medium, right? We're worse than the freaking fish. So, and I just wanted to say here that when the units are balanced so that time and distance have the same length, when you do geometric drawings of this, it's automatically that they balance out if you're doing it the way I do it, like throwing momentum vectors into the space, for space. But I like to keep, in this discussion where I'm doing arithmetic, I want to keep the traditional units of C where it's 299 million meters per second. And the reason I want to do that is because I like to retain the units, meters for distance and seconds for time, because it tells me which direction the momentum is pointing, and I don't want to lose track of that. And I also want to make it more difficult to get the exact derivations correct, because if you don't get the right amount of meters per second, because they tend to cancel out, cancel. But no, I'm keeping them in there, and there's much more opportunity to screw up. So it makes it much more, it makes it harder to do, but easier to get the right answer, and understand it correctly. So I'm keeping those for now. Oh, here's that part I was looking for earlier, where I want to just take a unit analysis. No, I hate that word. I'm taking the units, and I hate that word because the right-hand side of the brain, which is this side, no, this side. I'm looking, and it reverses it on the screen. Yeah, and it's synthesizing. It pulls things together. So when you're operating with visual, you'll notice that you don't like things like analysis, which is to take it apart. Even though you rip the hell out of it, in some ways you're synthesized. You're coming up with a synthesis of it. So so what I'm doing here is I'm looking at the units, and so I have the I forget which. This is permittivity, and this they call it permittivity. Remember, I don't like that. It's the capacitance, and this is the inductance of free space. Let's stick with that. I don't like the terms people give. They tend to always create obfuscation, needless obfuscation. So E naught, the capacitance of free space, has the units second squared times Coulomb squared divided by kilograms per meter cubed. Okay, it's the U naught, which is the inductance of free space, has the units kilogram meters divided by Coulomb squared. Coulombs is the number of electrons that I forget the number. It's not important, but it's a fixed amount of electrons. It's used like coulombs per second as the amperes. So that's not important here. What we're doing is looking at the units. Hence, if I take U naught and multiply by E naught, you get a components. I take the components and multiply them together. They cancel, and you get seconds squared per meter squared. The one in blue there. Seconds squared per meter squared. So that is the speed of light squared, up inverted. So in order to get meters per second, you would have to flip that, the u naught times e naught, and take the square root. Because when you multiply it together, you get the inverse squared, and you want to get rid of the square, and you want to get rid of the inverse. So the way you do that to get meters per second is you take u naught times e naught, and you put it on the denominator, not the numerator at the top. You put it in the bottom, and take the square root. So when you do that, and you take the numbers you measured in your garage, which I have up top here, you come up with 299,792,458 meters per second. Again, you come up with the speed of light. And that's how you calculate it using the measurements you perform in your garage. And you can do that anywhere. And if you're moving at a constant velocity, you can measure that anywhere in the vacuum, anywhere, and you always get the same result. Let's move this up. So I do this every now and then. I want to hit your mind with, or at least, let me not use that word, but it could be a shock, that's what I mean. A very concise, a kind of language. I'm going to be using language now, but with that same kind of almost Asperger's type of equality as an identity, the same. It means not just equal in amount or something. It means identity, the same identity. It's like I see you on the beach, and then I see you in the grocery store, and I go, you're so and so. I've made the equality of identity, not just the amount or the direction or something. So let's look at this. Now I colored it. I'm trying to go through the whole thing very quickly because I can state most of relativity right here in these 8 points. So I'm going to say it to you. Let's see how it balances. It's not critical that you get everything. Okay. So here's how it goes. We designed 2 simple apparatus, the ones I showed you that we had in our garage, to measure the capacitance, E naught, and the inductance, mu naught, of the vacuum. The vacuum is the same everywhere, so these characteristics will be the same for everyone and every piece of equipment in any local reference frame. So we've already been through that, and hopefully we agree on that. So then, number 2, in the red here, if one constructs an electric circuit with the same E naught and U naught as we measured in the vacuum, we know this circuit will oscillate at 299, something close enough to 300 million meters per second. Oscillate at, not meters per second. Well, yeah, it's true, it does. It propagates. It oscillates at 300 million cycles per second and oscillates for one chunk of the circuit, but it also propagates at 300 million meters per second. Okay. So that's the speed of light. You can get this directly from the units of E naught and mu naught, which we just did via a unit analysis. We thus know, number 3 in the blue, or bluey-green, we thus know that since the vacuum has the same electric circuit, that the vacuum will have waves that also propagate at c equals basically 300 million meters per second. In fact, we know that 300 million meters per second is the only velocity for anything. Any wave moving in that medium with that inductance and that capacitance will travel at that speed. We have thus determined the constancy of the speed in all c, and which is we identify with the speed of light, but it's basically the speed of everything in all reference frames, which necessitates special relativity in full. If you just operate on that one fact and draw which you're going to actually do, draw the diagrams and everything, you'll get all the special relativity. Okay. So the total speed of everything is always the speed c, but you can change. I've gone on to number 4 in the light green, sort of sea green there. The total speed of everything is always the speed c. but you can change the direction of that speed by adding momentum. So when you add momentum to something, anything, everything, it doesn't change the magnitude of the speed, but it can change the velocity by changing the direction of the speed. So it's kind of like a rotation. Okay, that's number 4. Number 5, when the Earth, which is like everything else, travels at the speed of light in passing, it is a rate of change of momentum for the local vacuum. Okay, so when the Earth, if you were able to stop in time, which we are not, we're in the local domain of the Earth, so we're traveling also with the Earth in the direction of time. And if we just stand still with reference to the Earth, like by having our feet on the Earth, we are both sharing that time direction, and all of our momentum is going in the time direction, the Earth and ourselves. So when the Earth, I'm on number 5 again. When the Earth, like everything else, travels at the speed of light in passing, so if for some observer that wasn't traveling with us, with the Earth, but just standing still in time, which we don't even know how to do yet. The speed of the Earth in passing at the speed of light is a rate of change of momentum for the local vacuum. So it's a rate of change of momentum, which is an acceleration, which by necessity, acceleration equals the curvature of space-time. So we know that the Earth, in roaring by the local space-time, will cause a curvature of space-time, a compression, due to the mass. Remember we talked before, the energy, mc squared, over the volume, the energy distribution, is identical to a pressure, a compressive pressure. Okay, now that, I'll have more to say about that, but that gives us basically general relativity in that number 5 there. Okay, 6. Special relativity can also be turned back on itself to explain induction as a magnetic effect. So you can't understand induction without understanding special relativity, because what's actually happening is the electrons on each of those conductors see the other as having a space-time contraction due to the velocity. This is at the heart of the special relativity. And that increases the electron density of the moving charges. And the only moving charges are the electrons. The positive charges of the copper atoms and the protons in the copper atoms are stationary. So it's only the electrons that have this effect. So you have a net increase in due to the increased charge density of the electrons, one with respect to each other, which pushes the conductors apart. That's purely a relativistic effect. So in saying you could turn special, you use that effect in your measurements to derive special relativity, but you can also turn it back, like I did, and use it to explain induction and explain magnetism. Turn it back, and it explains both ways. Okay. This repulsion is what we call induction because it is induced by special relativity. So that's the end of this number 6 here, which is the one in gray. Now we move on to the nice sort of robin's egg blue, number 7. The measurements of inductance and capacitance of the vacuums leads inescapably to the theories of special and general relativity in full. Remember, what was it, number 4 in the sort of sea green there. That one talked about curvature, so it gives us general relativity as well. So now back to 7. These theories also act recursively to explain capacitance and inductance. So you make the measurements and you get special and general relativity in full from these 2 measurements. But these theories of special and general relativity also can recursively go back and explain capacitance and inductance. In fact, it's the only explanation. So physics is like this. It's together. It's one thing. I want to just pause for that in a second. Let it sink in. Let's go on to number 8 for the moment. I might have more to say about number 7. The recursivity of our metaphors for nature ensure that we cannot separate various phenomena into independent silos of understanding. If we do so, we may gain in simplicity and speed of operation. In other words, if you act as a technologist and pull the things apart and just operate on do this, do this, do this, do this, you get that result. You know, when you multiply this by 3, you got to divide that by 3, you know. Sort of an operational type of knowledge without getting the grand comprehension of what's going on. You can gain in simplicity and speed because you don't have to think about it. But we will necessarily lose the power and versatility of comprehension. And personally, I'm one of these people who has to know, because I just have to know. That's the first thing. And most of us, it's an instinct, the need to know, and it varies in different individuals. And I think I got a double or triple dose of it. But what this means is you cannot, without impairing your comprehension, divide physics and science into individual silos without losing comprehension and ability and creativity and the ability to create. By doing, let's say, you could say, well, you're an electrical engineer. Well, yes, I did an advanced degree in electrical engineering. And I also worked in electrical engineering, designing components, circuits, you know, optics. But they say, what the hell are you talking about general relativity for in quantum theory? And I say, because I have to. I can't understand electrical engineering without understanding general relativity and special relativity and quantum mechanics. And they might also say to a person like myself, why are you interested in biology? You're not a biologist. What do you know? And maybe I have enough time to tell you another story. I might have to shorten this talk, but I think this is important. To make a decision here. I'll go on one and let my brain process that. So I'm about to say we will require several results from uncurved space, which is space without accelerations. But I remember what I was going to say. It's quite a jump. I'm trying to bridge something. Yes, I was trying to design a flywheel that would store energy and would not fly apart and explode. And I was very bothered by the fact that, you know, if you put it in a car and the car hits a bump, it'll break and explode and kill everybody. So you have to build this basic confinement structure all around it. If you put it in your backyard, you have to build a little bunker so that when it explodes, because it will explode, the bearings, even if they're magnetic floating bearings, any little oscillation or a piece of dust or something on it, things wear out. So I started to say, what if I shrink the disk and make it go faster? Shrink it and make it go faster. Shrink it and make it go faster. So I went on this thinking process, and I kept on finding it. Every time I shrunk it, it got better and more efficient and faster. But, you know, it started a little frightening, but small. Until I realized, oh my God, I've just created an electron flying or circling around in a hydrogen atom. And so my thinking about machines which I'd associated with, tangible, graspable items, components, and had kind of shrunk down to such a micro level, atomic level, were machines. And then you put the atoms together into molecules, and those are machines and quantum mechanics. And, I started to be able to have an intuition, deep understanding and appreciation for those things. So it also brought me to deal with topics like biology, because and I had the title of my YouTube is I got to remember it, Hacking the Human Time Machine. And so for me, biology, and it's still mostly electrical, and it's still a machine, so it's mechanical, it's electrical, and I resonate deeply with those molecules. And people might say, well, why are you talking about biology? You don't know anything about biology. And it's like, yes, I can't just separate. I can't tear science apart into isolated silos. It's one thing, And I just wanted to say that. I almost lost that for a second, but I got it back. So we next go on. We will require several results from uncurved space, which is space without accelerations. Okay, so I need a couple of points before I go on about about our discussion of relativity. I need a couple of points from special relativity, and I put you through quite a bit in the last few charts. Some of this stuff needs soak time, so but I'm going to take it easier on you, I think, in the next few slides. So let's take two momentum arrows, which throw them into force space, and they land. I'm going to move myself here. Okay, there, two arrows, and at random, I just throw them. If you throw any two arrows down in space, they're going to, at least looking at it, they're going to cross. Let's put them on a plane where they cross, and so there's a plane. They define a plane. Okay. We start by throwing two arbitrary momentum arrows into force space. The two arrows define a plane containing both of them. Yes. We will restrict ourselves to showing only that plane, which is enough. It's enough for our discussions. The reason it's enough is the same reason I couldn't save my daughter right away from that dog, because matter only goes in one direction at a time. So if we look at one direction, that gives us a very powerful understanding. So what we do is I want to know on the green line the distance from point B, the shortest distance, to the red line, anywhere on the red line. What's the shortest distance? And the way you do that is you take a string and you start unspooling it and going around and around the circle until that circle just touches the red line anywhere. And that at the point where it touches, I put a dot and I call it G. Okay, so that's the shortest line. It turns out that for these, remember these are two momentum arrows, which means that they're both traveling at the one speed, determined by the inductance and capacitance of free space. And it turns out for quantum mechanical reasons, which I'll discuss later, probably much later, that line between B and G is the distance between B and G, and that's what it is. The distance between B and G, according to the green, someone riding on the green momentum vector. It's the point. It's the only place where the quantum mechanical waves sum up, and where matter can be evoked as an experimental phenomena. In other words, when you look, that's the time. B and G are the same time are simultaneous according to H. Now, okay, let's go on. Okay, so I drew a blue line. What did I say here? We draw a red line connecting B and G. We did that. This is the shortest distance from B to the blue vector. It's the blue vector from B to G. I should put up there to G. Yes. The blue vector, the shortest distance happens to be at G. Yes. The BG line is the distance dimension for any observer riding the green momentum vector. We said that, but it's good to say it twice. And it's from quantum mechanical reasons. So here we get the first inkling. We're only at special relativity. And we have a quantum mechanical reason for the space dimension, according to the person riding on the green arrow, the spatial dimension, when the person in the green arrow, which is going to be his time direction, because that's when you're matter riding on a momentum vector, that is your timeline. So from B to G is the distance from B to G, and B and G are simultaneous according to the guy riding on the green arrow. Okay, so now we do the other thing, starting now on the red line. I start with line G. And you say, well, for most people, including myself at one age, you ask them, okay, so the shortest line, according to the guy on the green arrow, from B to the red line, is, I'll tell you, it's BG, the line BG, that blue line. Well, it's red, it's blue actually, underneath. So BG, the line BG. And I say, well, okay, well, the guy riding the red momentum vector, what is the distance from his point G, the shortest distance over to B? And you'd say, well, if the shortest distance from the green line at B is BG, then if you want the shortest distance from G on the red line there, it has to be BG again. Well, that's what you might think. But if you actually do the experiment and you take the point G and you progressively expand the circle till it just touches the green line, you can see it right here. The circle just touches at the point A, which is not B. So, and for the guy riding on the red line, the orange line A, why, that is the line of simultaneity and the distance from G to A according to the guy on the red momentum vector. A different distance line relative to the green line. So for the point at G, riding on his red timeline, the simultaneous time over on the green line is the point A. And if you look, you can see that on the green line, the distance from H, where all the lines cross down there lower, to H to B is greater than the point H to G on the red line. So the guy riding on the green line says, well, my time, I've got through more time than the guy on the red line. The distance HG is smaller than my time HB. And that's one way of looking at things. But the guy riding on the red arrow says, well, wait a second. I did the same experiment from my point of perspective over here on G, and I find that my time, my clocks, is HG, and the same time over on your side there is HA, which is shorter than my HG. And so they both say, well, one of them says, your clock is slower than mine. And the other guy says, no, your clock is slower than mine. And you know what? They're both kind of right. Now, most people won't tell you this, but the real truth is that these momentum vectors are going along. They're all traveling. Both of them are going at the speed of light. And which one has they're both has gone through the same amount of time, according to their local clocks. But this thing that I just brought out, the way that they perceive the other guy's time is slower is due to their perspective, which is a function of the rotational angle of these vectors, one with respect to each other. Now, I want to make a jump from slide 20 to slide 24. I say that so I don't forget. Here we have, excuse me, I'm showing H and O, and I'm showing this just how symmetric the condition is. Like, both have gone the same amount, and both see the other length as shorter. And this, I turned it up and made it vertical, the center line there, just so you can see that it's a symmetrical arrangement where, and their different perceptions of the other person's time is totally a function of their perspective, their angle due to the rotation of their momentum vector with respect to the other momentum vector. And you can always arrange it so it's symmetrical. And this is for motions that, excuse me, have no acceleration. This constant motion, which is special relativity. So I'm going back again to where I was, slide 20. I'm going to slide 21. Okay. So we make a distance vector along the red person's line. Okay, that's that brown thing, I think. The distance from H to K. Oh yeah, the lower brown thing, HK, as the distance. And then as the red momentum progresses in time, that same distance, HK, becomes at a later time, the later time HG, look at it yourself, that distance is now GF. So it goes from HK at point H to GF at point G. Okay. So now the distance this is the distance according to the person in red. Yes. This distance could be the diameter of a planet, for example, or any other physical distance as measured by the red person. Now, we let this at a later time, GH, according to the red person, we show this same distance now as GF. Okay, I said that twice, which is good because it allows you to get it twice, get two shots at it. So we make a distance vector along the green person's distance line going through H. Okay, that's in the bottom there, H. We also put a distance line according to the green person going through point F to where it intersects the green momentum at point C. So what we're doing is we're going along the distance line according to the person on the green arrow, and we're connecting the point F, which that might be like an event where maybe a little explosion occurs or something at that distance from G, GF, according to the guy in the red. And we connect that way up to using the distance line according to the guy riding the green one. We connect F to C there at the top on the green line. So what we get is this distance EF. Well, that's the distance from the red vector E to EF is the distance within, like that might be the planet, that's the width of the planet according to the red guy riding the red planet, right? And whereas the guy riding the red planet, according to him, it's GF, And according to the guy in the green, it's EF. Now notice, the guy in the green sees that EF is shorter than GF. You can just see that. The guy in the green, right in the green, sees that his planet is a little squeezed in the direction of motion. And we see that here. So, according to the guy in the green, and the guy living on that planet doesn't notice anything because he's just riding the planet, and whatever direction it's going, that's his time direction. So that's actually how it works. So I need that value. I need that ratio. I need the ratio EF to GF, because that's what do they call it here? It's the boost. Yeah, the relativistic boost factor. So I just do, I take the speed is equal to BG divided by BH. Okay, so BG, where's, okay, that's the speed according to, between it's the angle basically, is actually the speed between the green vector and the red vector. So the speed is EG over GF, and so GF over EF, and we notice that these are similar triangles. I have more to say about that. Similar triangles. So if I know that the ratio on similar triangles is always the same, and the ratio of the sides, no matter if the triangles change size. So from that we get that GF divided by EF is equal to GH divided by AH, and so that when you rearrange that, you get is equal to 1 over 1 minus BG over BH squared to the 1/2. So we've just worked out geometrically using similar triangles that function there. So the proof, I'm jumping down to the next box below. Proof, and then I actually do it. EF is equal to GF squared minus EG squared to the 1/2. That's using Pythagoras. EF over GF is equal to, I rearrange it, 1. I take I divide both sides by GF, and I get on the other side 1 minus EG over GF squared, 1/2. And then EG over GF, we already discovered up above that this is the velocity, so we get the velocity squared. And this is in natural, since it's a geometric diagram, everything's naturally balanced from one to the other. And it means that the distance and the time are actually in their proper balance. So the speed of light is 1 under it happens automatically. So in some analysis, you'll see v squared over c squared. But since we're using a geometric diagram where it's balanced, the c squared is 1. So you don't see it there, but it is there. And we end up with the final result, GF over EF. So what GF was the distance according to the guy riding the red planet, over EF, which is you can see it right there. It's the distance according to the guy riding on the green momentum vector. And that's equal to 1 divided by 1 minus v squared all to the 1/2 square root. And that they call it the relativistic boost factor. Now if you look, it's 1 minus something on the bottom, right? So if v squared, let's say, was 1/2, then you get 1 minus 1/2 is 0.25. So it's less than 1, and you take the square root, and it goes up a bit, but it's still less than 1. So it's a boost. It's in the denominator. You put something less than 1 in the denominator, it's a boost. It's bigger than 1, because put anything small in the denominator, it makes the division greater than 1. So they call that the relativistic boost factor, and I'm just showing you where it came from. And again, I think take a screen save of these things, or play it back and forth a few times, and you'll see it. So let's read what I have over on the right-hand side here. HK, which is on the bottom there, the H and K, you can see that, and equivalently GF is a distance according to someone riding on the red momentum line. The corresponding distance for someone riding the green momentum line is the distance EF. You can read that right off the diagram. EF go to E, which is on the red line, and then go down a little bit to the write more, and you get F. So the corresponding distance for someone riding the green momentum line is EF. You can see that EF is shorter than HK. So we know that EF is shorter than HK. Right, you can see it on the diagram. So it shouldn't surprise you that GF over EF, where EF is smaller than GF, is going to be greater than 1. And that arithmetic with Pythagoras demonstrates that. So we just proved it I threw two vectors, and they landed and they crossed each other, and I said that's the plane of motion, and we just played around with it a little bit, and we get the relativistic boost factor, which I need. I didn't do it for nothing. I need it later. So here I'm showing again here the fact that none of these two reference frames are special. Each sees the other guy as having the same shrinking or expansion, depending. And they're both really experienced in the same time, and the differences that show up, one with respect to the other when they observe, is due to the perspective, due to the rotation of the vectors with respect to each other, the momentum vectors. So let's continue on a little bit. Oh, you know what? I think the next one is unbelievable. So I'm gonna now, since this is the first time I did this, I'm gonna call it quits right now. And I'm gonna thank you very much for what, I'm sure at times you got your brain working, and at other times it's a little exasperating to see so much so quickly. But hold on. The next chart, I examine the twin paradox and show what's really going on. And it's amazing. It's one of those things that just I'll show the reality of space-time and time travel and how we do it every day, a small amount, and why we don't notice it and everything. And what I say, any scientist will agree with. But I haven't said it yet. We're going to say that next time in the presentation number 2. So stay tuned and look for that. And again, I thank you very, very much.